In this chapter, we move from the idea of a random signal to the tools used to analyze and filter it. First, we define a random process and describe a signal as one realization of that process. Then we build the statistical description: first order statistics, second order statistics, and stationarity. After that, we connect time domain correlation to spectral content through the power spectral density and the Wiener-Khinchin theorem. Finally, we look at sampling, random signal filtering, Wiener and adaptive filters, and a few classic spectral analysis and parametric models. A random signal is an observation governed by chance, so its instantaneous value cannot be predicted exactly. The key idea is that the signal we see in practice is one realization of a broader random process. If we look at several time instants, like t1 through tk, the process gives us a set of random variables. Together, those variables form a random vector with a joint probability law. This is why a voice signal, for example, is not treated just as a single waveform, but as one sample path drawn from an underlying process. The chapter then splits the description of a random process into two levels. First order statistics look at one time instant at a time: the cumulative distribution, the probability density, the mean, higher moments, and the variance. Second order statistics look at pairs of time instants. There, the process is described by a joint distribution, and especially by the autocorrelation and autocovariance. In practice, first-order statistics tell us about the amplitude distribution, while second-order statistics tell us how values are related across time. Stationarity means the process does not change its statistical character over time. In the strict sense, every statistical property is invariant under time shift. The distribution of x of t and x of t plus a constant is the same. Second-order stationarity is weaker and only requires the first and second-order statistics to be time invariant. This matters because, for stationary processes, the autocorrelation becomes the key summary, and the power spectral density can be obtained from it. The periodogram is a finite window estimate of that spectral density, but it remains random because it depends on the realization and the window position. Averaging several periodograms or using the correlogram reduces that variability. The next step is to move from continuous time random signals to sampled ones. Sampling takes one value at each instant, so the result is a discrete random signal made of random variables indexed by n. If the original process is stationary at second order, the sampled process keeps that second order stationarity. The chapter then turns to linear time invariant filtering. For a random input x of t, the output y of t is still random, but its expectation and autocorrelation can be written in terms of the filter response. When the input is wide-sense stationary, the output remains wide-sense stationary as well. So sampling and LTI filtering preserve structure, but they change how that structure is expressed. Once the chapter has set up filtering, it asks for the best linear filter in the mean square sense. That is the Wiener filter. The design goal is to minimize the mean square error, and the orthogonality principle says the optimal error is orthogonal to the observations. In practice, solving the Wiener-Hopf system directly can be difficult, so the chapter turns to adaptive methods. LMS replaces the exact gradient with a stochastic approximation and updates the coefficients iteratively. RLS goes further by using a recursive least squares approach, which converges faster when the data are poorly conditioned. The chapter ends by comparing several ways to analyze random signals in the frequency domain. The non-parametric side includes the simple periodogram, the averaged periodogram, the smoothed periodogram, and the correlogram method. Window choice matters because a rectangular window creates side lobes, so Hamming or Hanning windows are used to reduce them. The selective filtering and scanning analyzer ideas show another frequency analysis viewpoint. Then come parametric models, Gaussian white noise as a starting point, forming filters, and the AR-MA and AR-MA families. These models describe how a process can be synthesized from white noise. The final matched filter idea is important too. When a known signal is buried in white noise, the matched filter is the linear filter that maximizes detection performance. And that concludes our look at Chapter 3. We've journeyed from the probabilistic foundations of random processes to the practical tools of spectral estimation and optimal filtering. Understanding these relationships between time domain statistics and frequency domain content is the key to mastering modern signal processing. Apply these tools well, and you'll find patterns in the noise.